checking time. 傅陆云、赵佳琪、灰家园、陆一凡、姚如歌、李东浩、瑞奇、沈南、Dean, it's not here. Tuna, Lexi, okay. Last week we tried to demonstrate the antenna arrays. Arrays, and we said first what we need to consider is the for an isolate element, its electric field or the radiated electric field E phi can be expressed by the first term is the spherical wave E minus J K. And also times the factor f. Right? So this is the directional element, directional dependent f, the smaller case f. And it depends on, or it is going to determine the direction of the total beam. And also the corresponding power density. Equals to node. Also the B. Phi, right? So square expressed and then finally it can be expressed as so beta node r square more and f square. Alright. Okay. So this is just for an isolate element. However, if we have for an array, so it has, for example, n elements. For n elements, for each one of it, it can be expressed, for example, ith element. Expressed in I, right? R, theta, y, the same thing. Expressed as I and E minus J K I times E theta phi. So here, for this part, for such an antenna array, we assume that for each element it has the same directional element. And also, of course, we need to consider the fading coefficient. So here times AI, right? The complex fading coefficient. So it can be expressed as AI equals the amplitude times the phase part. So for such an assumptions, what we have is we use the such, for example, we have an antenna elements, so we use circles to represent that. So this is the element node, element 1, element -2, element and -1. So we have n elements, and for each of it related to the amplifier or attenuation element. So this one, and this one. So, okay, we use the squares to represent that amplifier or attenuator. So this is a node represented through the amplitude here. So we note 1, n-2, and n-1. And also before that is the phase part, right? So we have our phase part, the phase shifter. Phase shifter, and we call it psi n-1, psi n-2, psi 1, psi node. So this is the this is the real element, the individual amplitude and phase connecting. Okay. So for the what we should notate is that the Ri and Ai can be different for each element. For each element in the array. However, the directional part should be identical. For each one, and so they should exhibit identical the patterns. So now, if we set the elements, for example, we assume we have the dipole antennas. For each element is dipole. They can be dipole or colon, rectangular, many kinds of such antennas. But for here, if we assume the distance for each element between two neighboring elements is d, okay, and the total length L can be represented as how much? We have n elements. It's capital N minus 1 times d, alright? So if we assume that we have a Cartesian coordinate system, this is y, and this is theta. And so our observation point located here, and call it Q. So Q is related to the R node. Its distance to the origin of the system is R node, and the theta phi. Okay, so this is our node, and this angle we call it theta. So this is an important angle. So and this distance is our node, and also we call this distance it's R1, right? And here is R7 n minus 2, and this one is minus 1, alright? So the distance. And so what we can do is, for the total electric field observed at position or at point Q, it can be represented as the E theta 1. Here we use R node to represent the total the distance of the whole array to the point Q. It's just we just consider for the approximation, because the point Q is in the far field region or the far zone. So it can be expressed as the electric field for each element, right? And the I R theta phi, right? So the -1. So previously we said we have the +1 elements, but here we said only has the -1 elements, right? So the procedure I want to show. Well, you can just look back your note for Monday. So finally, the electric field is represented as E theta phi, right? And times the spherical part minus R node. And also there is another part that's inside. 0 to -1, and I, E, J, I, K, E cosine theta. Alright, so I'll think about this one. And we assumed this part as the array factor, right? And use the array factor is related to the power density, and it's related only to theta because it is symmetric with respect to the azimuth angle, right? So I equals node to n-1 AI. E J I P E cosine theta squared, right? So this is the array factor, and so finally the power density SE R node theta phi course. S not S. So S equals SE the R node theta phi times the array factor theta. So when we come back to the so SE is the power density generated by an isolated element, right? So it's let's look back to this part, right? So this part looks like this one. So this is one isolated element. So we do not need to consider the whole array, just consider one element. So it equals the absolute value square of the absolute value of this part, right? So this is the power density by an isolated element, and then multiply the array factor, and this. Now, then we can get the power density generated by the whole antenna array. So here we need to consider what we need to take care of. One point is here we consider this as the far field region. So for near field region, this condition will not work. Okay. So this equation also demonstrates the pattern multiplication principle. Pattern multiplication principle. So what it is, so-called the second principle. Pattern multiplication principle actually needs to consider two parts. The first part is for an antenna array. The first step is computing the far field pattern, power pattern. With the array elements. Replaced by isotropic elements or isotropic radiators. And it's going to generate the MPC, the array factor, and also then multiply the results. The phase vector, the power density for a single element. For a single or isolated single element. So now, as we know that the fitting coefficient I can be expressed as amplitude times Ej psi I, right? So complex value. So then it's gonna determine related back to the array factor. It's gonna relate it to two parts, right? One part is the amplitude distribution. Another part is the phase distribution. So it is called array amplitude distribution, and also the array phase distribution. So the amplitude distribution serves to control the shape of the pattern, all right? And the array the phase distribution used to for what? You remember? Steer the direction, right? Steer the direction. So now we know how to control if we are not to design an antenna array for our aims. We know how to control the pattern and also direction of it. So, now let's assume a uniform phase distribution. So first, it's the uniform phase distribution. Phase. So for uniform phase distribution, which means for each element, the phase part, of course, a constant Then, as we all know, the refactor, right? Refactor. Previously it equals here, right? So the refactor equals this one. AI equals AI E J sine node, alright? So this becomes constant and it can move out of it. So it equals E J sine node and absolute square. Alright, so inside is I equals node to minus 1 AI E J K J I K D cosine theta square. Right? So this part, which means if it's uniform, this part means the absolute value equals 1, right? So we can equals 1. So we have the following part like this one, and so we can also define what. So previously for the electric field, as an example, this part is the KD cosine theta. Do you remember how to obtain that? Of course, the KD cosine theta is conducted from the phase difference at point Q from the two neighboring radiators, right? So it's related to this part, right? D cosine theta. So it's due to the path difference related induced to the phase difference. So the phase difference we can define a parameter called gamma. The phase difference to neighboring or to adjacent elements, this can be represented as K, alright? The phase difference K times the path difference cosine theta. Can also equals to ID divided by lambda times cosine theta. This way. Then our array factor can be represented as I equals 1 to 1 equals node to n minus 1 I E J I gamma square. Alright, so why we wanna use a phase difference to represent this part? Because it's more convenient for us to conduct further conductions or calculations based on this. So for the uniform amplitude distribution, and because I from node to n minus 1, so finally it becomes 1 plus E J gamma plus E J to gamma plus things, right? So E J n minus 1 square. So this is the to further simplify the calculation, we can also define another parameter to represent this part. So we use the small case A gamma to represent that. So here, because we represent we use this one, so it becomes gamma again. Okay, so it becomes so A sine square with P equals this equation. And then also finally, after the calculation, it becomes sin then gamma over 2 divided by sin gamma over 2 square Oh, just this one. And so this one equals C square. So based on this, now we can calculate or we can plot the pattern, right? Even though we do not consider the element amplitude, but we can get the pattern based on this one, a normalized pattern. If we want to get, so here is the uniform amplitude and phase. And this. So, however, we really need to plot the normalized. So, for normalized, which means so F8N represent normalized, comma, and equals the initial pattern divided by, for normalization, divided by what? The maximum, right? For normalization. So the maximum of it. So for this equation, the maximum of it should equal to how much? How much for this part? Maximum. So let's come back to the this plot. So if a cube, its position is random, okay, it can be changed. So let's assume here it's gonna get the maximum radiation. Detected. Which means, because here we assume this is always theta, okay, because its proximity R is much larger than D, okay. So we can assume that all of them should be parallel to each other approximately, and if we want to get the maximum radiation, which means theta should equal to 90 degree, right? 90 degree means all of them are parallel to each other, and they can just add it together, do not consider the phase difference between them, and they're gonna never modulate the radiated pattern, the radiation received by the observer. So from here, it's the same thing, which means theta equals 90 degree, this part equals 0, alright? So let me just come back to this equation for an example. So for such an equation, is if it one gas its maximum value, which means, let me plot it. If you plot it by the programming, and you can find that when it reaches to 0, it's going to return its maximum value. For this part, it reaches to 0 means it equals to n gamma square, alright? It's linearly the same. Theta equals roughly equals theta. So this is 2 gamma half gamma square equals n square. Alright? Correct. So which means finally, the maximum is the addition of all the elements, just a geometric addition of all of them. All right, the algebraic addition. So, which means the max, the normalized dimension is n squared. This. So, what we consider is now we get the expressions for the normalized reflector. So we can then plot our pattern for certain conditions, and also for such uniform. Remember that we consider as the uniform phase distribution with psi are the phase part set it to be a constant for all the elements, and the radiation pattern is called broadside. Broadside pattern. How it can be called a broadside pattern? So let's plot it again. This one. So this is x. This is beta. Right? We come back to this plot again. This array, such array, and this radiation looks like. And here we set, for example, we have 7, 6, 7. They assume we have 7, 2, 3, 4, 5, 6, 7. Their separation is identical, okay? Just close the So the pattern generated looks like the Menlo here, and has several side lobes. Also has the side lobes. Okay, so this is broadside because it's distributed over the whole thing, half of the whole thing. So this is broadside, and here when it has limitations on the separation distance between each of them. When we assume it is a part of the lambda, half of lambda. So, however, if we want to change the separation of each element, so d equals half lambda, which means this part gamma equals 2 pi d over lambda cosine theta equals pi cosine theta. Am I correct? Because d over half lambda. Alright, so this is the gamma varies with respect to such condition. And so theta, for theta it varies from 0 to pi, alright? So theta from 0 to pi. So now if we wanted to increase the separation of each element, then x and theta again. So their separation is increased. triple of the previous one, so 3 lambda half. And then now the radiation pattern is going to be different. It becomes narrower. And becomes the side lobes also narrower. This side also the same thing. Here I have another peak. This one. And then narrower. Okay, like this one. So why it becomes like this? And such such a kind of pattern and all the lobes, the grating lobes. So, because we get our main lobe, it is a repetition of our main lobe, like this one. And so why this generated? That's because when we come back to the gamma, now it becomes 2 pi d over lambda cosine theta. It equals d over, it becomes 3 pi cosine theta. Alright? So that means this parameter it was enlarged, right? Which means it was enlarged. So its main lobe is gonna be repeated like this one. So here, why we choose d equals half of the lambda? This is the situation that we want to set to restrict it. So actually, for the grating lobes, if the grating lobes, we want the grating lobes to be spaced far away from the main lobe. Actually, for example, we would want our power more concentrated in the main lobes, right? So more likely, more like this one, right? So we need limitations to restrict or limit for the distance between two adjacent or the neighboring elements. So for such conditions, that means the restriction gamma equals phi d over lambda cosine theta should be smaller than 2 pi. And then main lobes or the grating lobes gonna be moved to this side, to this side, this part, like this one. So what we need to do for this, if we wanted to set the main lobes as what we needed, and so we need to restrict the distance between two adjacent area elements, and this is that part, and so the maximum actually d for the minimum d can be vectorially corresponds to 1 cosine theta equals 1, for example. The d is related to the wavelength, alright? So This is a consideration for that one. And also, we further considering that. So if we wanted to introduce the phase delay between these two adjacent elements and to steer the antenna, the beam direction, what we need to do is the distance d should be smaller than half of the wavelength, and then we can get to the efficient controlling this part. And this is also related to the theory. What theory? Do you know? Nyquist sampling theory. Anomalous to this one, right? To this part. So, however, if now we know how to design the distance of separation, and how about if we wanted to squeeze all these side lobes and enlarge the main lobe? We need another consideration, because we wanted to change the patterns. If we want to change the pattern, what we need to do? The shape of the pattern. We need to change the amplitude distribution, right? The array amplitude distribution. So here it is. So we need to change the array amplitude distribution. So which means we need to change AI, distribution of AI. So here, when we set the amplitude distribution, AI follows a binomial. Which means AI can be represented by an equation I dac and I divided by I dac I minus n minus I minus 1 dac that. So this is a binomial distribution, and so we want it to reduce side lobes. So now we know that if still when we come back to the previous when we come back to the 7 elements, the array has 7 elements, A capital N equals 7. So the A node equals A6 equals 1, A1 equals A5 equals 6, and A2 equals A4 equals 15, and A3 equals 20. So now when we get the array factor, say gamma equals get the expressions for that, right? So H1 plus 6 plus 15 E jack 2 gamma plus 20 E jack 3 gamma plus 15 E jack 4 gamma plus 6 E jack 5 gamma plus 1 E jack 6 gamma square. Okay, let's take a short break and then we can come back and continue. 好，我们休息一下，再回来，再回来。
军舰理论所。下午1点给我。1月开始，人员成本业务很难在努力上升，一点我可能还在这个位置上去，太困难了。昨天晚上在公园看到10点半，一轮还好。对，我也没说。昨天半夜那个下班有个啥东西在那个上头玩12点。
我昨天晚上2点多还没睡着。
我昨天1点多睡，我2点半的时候还在听楼下他们打电话。
So after that, we can get the expression, the expressions for the array factor, like this one, and transfer it to the same cosine function. We can plot the patterns for that, and slide it. And the condition of this one, it becomes like normalized. Looks like this one. Its beam width becomes wider, but its side lobes are all squeezed away. So, like this one, the trade-off, all right? Part of the lobe and the number of side lobes. So, this is the demonstration on the pattern distribution, and then next we need to consider or analyze the phase distribution and just see how it is used to steer the beam direction. So, scan. All right. So we use the phased array to steer the beam direction electronically instead of mechanically. The course. Okay. It gives us a faster beam switching, the faster rate for beam switching, right? So this is the most or the biggest advantage of the phased array with respect to the mechanical scanning system. So here we also need to see the array. Here we assume that now, because previously we said it is a uniform scan, and we said psi I equals a constant for each of them, right? So now here, this one is the phase distribution. It has a distribution, that means it cannot be a constant always, right? So it has a distribution here. The firstly, we assume it is a linear phase distribution. So first, assume the psi node equals maybe a node, and psi 1 equals minus theta, and psi 2 equals minus 2 theta also, and psi and minus 1 equals minus 1 times theta, minus the upside minus 3. So the phase of the arrays is I equals minus I times third, right? So then what we should do? We need to come back to the original expressions for the array vector, right? So it can be represented as +1 and -1 is here absolute of the I E minus J K E J I K D cosine theta square, and so of course 1 to n minus 1 AI equals AI E J psi I, all right? Psi I equals minus I theta J I K D cosine J K D cosine theta square. So we can combine both exponential parts, and I equals 1 to n minus 1 I times E, right? Ki of the J I times K D cosine theta minus theta, Alright? So previously, to simplify the expressions, we said previously, let's come back to the expressions here, right? So we switch it from this equation to this equation. We assume gamma equals kd cosine theta. So then for here, gamma equals kd cosine theta, right? Then we assume another gamma prime equals kd cosine theta minus theta. So now at A, the array factor becomes prime equals I equals 1 to n minus 1 if I j I gamma prime squared. Okay. Now we get the same expressions as for the uniform array. Alright. So we can plot if it varies with respect to gamma prime, it should have the same and with a uniform distribution, and if we can get the same expressions like this, right? Am I correct? So if it varies with respect to the gamma prime, actually, I think it varies with beta right physically, right? And it is fixed angle, or the zenith angle. Sorry, the zenith angle. So now to make this expression more symmetric, we assume, because it's related to the zenith angle, right? And the wave number times the separation, and then times the zenith angle. So we can want to express it the same thing, kd cosine theta minus, because theta is related to the geometric structure of the array. So it is constant. So we can assume it as k times d times cosine theta. So that means theta equals. That means this theta equals this part. So okay. We transform the phase delay of the phase difference to the angle range. So with respect to the angle range, then that means when we change the delta or we change the cosine theta, note we can steer our wave direction, and we're going to show that later. So now gamma prime can then further be changed to PD times cosine theta minus cosine theta, no, like this one. So now we have the expressions for this one, and it varies with respect to that one also. So now what we can do next is we need to analyze the variation of the beam direction with respect to the angles. So previously we set when we set the for uniform direction, which means psi I equals psi naught, right? And if we set it to be, for example here, so for this equation, if we want to get the maximum, or if we want to get the maximum direction, so the beam direction, right? The actual beam direction. It's related to theta equals half pi, all right? That means gamma equals from here, gamma equals node, all right? So equals 0. So we can get the maximum. But for here, if we want to get the maximum, so gamma prime should be equal to 0. But here, if gamma prime equal to 0, that means the angle theta can never be pi over 2, alright? It should equals the theta node. So later determined by the phase distribution is set. So that means the main beam is changed. The direction of the main beam is changed, actually. And also, if we want to change the main beam to other directions, then we can just change the theta node, alright? So change the theta node and you change the phase difference delta. You can steer the beam direction. So for an example, when we come back to, so if we want to get the same pattern like this one for the non-uniform distribution of the arrays, what we should set? Because here gamma equals this one, it's related to this one, and with respect to get theta equals pi over 2, alright? So what we should do, we can just set theta node equals 0, right? Then theta node equals half pi, alright? Then the delta disappeared, and we can only have this part. So this is for this part. However, if we change the theta node from pi over 2 to 0 degree, what is going to happen? First, the beam direction is going to change, alright? If this is correct, definitely. And also, so as beam width going to be changed also. Actually, previously we said that because the shape of the power pattern is determined by the amplitude distribution, right? Determined by the amplitude distribution. But here, because the phase distribution changes gradually, and the beam width can also be changed. Actually, the side lobes or the variation of the side lobes will not be changed, but the beam width can be changed like this. So when we change, or when we switch, or when we want to steer the beam width from, for example, plot like this. Let's say, for example, let's make like this one, like this. and when we want to change change it to, for example, to this direction, or to this direction, this one. So when it is switched to other directions, for example, its beam width is going to be enlarged. If you plot if you plot this equation, if you try to plot this equation, you're going to find that you're going to change our base here to here to here. This is theta node equals 0. Theta node. So this is the beam steering for that one, and also the patterns only depends on the amplitude distribution and also the phase distribution. It also determined by the shape of the antennas, all right, for each element. So as we mentioned previously, the element can be horn or dipole, dish, antennas, and for each kind of antennas, you're going to have different radiation patterns also. So here we introduce several kinds of antenna types. So for the antenna types, it's usually chosen based on the radiation pattern we need, right? Firstly, the radiation pattern. We need, and also depends on the gain polarization, and also the bandwidth and impedance. Something that one also determines some kinds of things. So first, with the whole antenna. Which are commonly used, all right? That's used, example, in the dark room for the experiments, and they use the same kind of systems. And they are also, if we maybe enlarge the gain of the system, we use the reflectors, all right, and combine the reflectors to increase the antenna gain. So the whole antenna, it provides a gradual transition between a waveguide and the free space, all right. So just turning this waveguide and the horn, and this is free space. So the transmits from the waveguide to free space. So it usually support only the dominant the propagation mode. Purely, and then antenna square, if we want to get maybe, for example, we want to squeeze or just avoid the higher order modes. What we can usually do is we just flaring the terminal section we got, right? So sometimes maybe, even though they operate at the same frequency, and you can see some antennas is much longer, and this is shorter, and so something like that. And, however, we have a kind of the antenna is pyramidal antenna horn. Pyramidal horn, and usually looks like the cross section of it. Looks like this one, right? This one. This one. Pyramidal horn, and it is usually used as a standard gain horn. Why it is called a standard gain horn? Because it can usually be used as a reference antenna for the measurement. Used for a reference antenna for calculations. And also, if we wanted to, for example, here it's just we wanted to enlarge, or we can change it to the sectorial horn. Why enlarge is maybe E-plane or A-plane. Then you're gonna see some horns that like, right? See. The if along the A-plane is the same length, but for the A-plane is enlarged. Or we can call it a layer. And also for the H-plane, sectorial horn, and like this one, just the H-plane is only the H-plane is layered. Like that. And this is the E-plane sectorial. And this is H-plane sectorial. And also, we have another kind is cross section as a circle, right? Circle. So this is canonical horn. Which are more commonly used, right? Because perfect whole circle, and they can give us a more symmetric radiation patterns. Symmetrical radiation pattern. You can give us. So that kind of antenna is very commonly used. And also, the canonical horn are also used to maybe achieve the different kinds of radiation patterns by the reflectors, right? So, for example, what we already used is the Cassegrain, all right? Cassegrain antenna or the Cassegrain system. For example, is light reflector, and we have the horn feed. And then we have another one, right? So this side, same thing. Right, so this is clustering, and also if you want to move the fading part, is much closer to the main reflector. So this is a parabolic. Parabolic main reflector. Why we do not use spheric reflector? We use parabolic because its focal point is exactly for all of the directions, right? The focal point is fixed. But for these spheric reflectors, there is a little bit difference for each line. The focal point is going to be a little bit difference. So that means the collimation gonna be cannot be a perfect equation. And also it can also be combined with other kinds of reflectors. For example, the front fade. The front fade means, okay, this is the reflector or the main reflector, and the horn is here. Okay. Then related this one. And also there is a horn reflectors. Let me put the horn here. Right, so all these determines by reflection of our situation we need. So this is for the canonical. So actually the radiation for a circular waveguide, if it is faded with a circular waveguide, or it is connected with a circular waveguide, and purely set it. So, for example, a circular, it is faded by a circular waveguide with the TE1 mode. Right, like this one, and its directivity is determined by actually, yes, it depends on the wavelength, right, or the frequency. It also determined by what? The geometric structure of the horn, all right? Correct. So, for example, we have a horn. Okay, and here is this length we call it error node, which represents the x length, and it also such length LC or H slant length. So definitely has a aperture, right? This aperture is another length. This length is D. Okay, the aperture distance. So now the directivity is determined by all these three parameters together. So firstly, is let's determine the canonical hole. The directivity determined by, can be expressed as 20 log 10 id over lambda minus correction constant. Okay. This is for the optimum. So, if we want to get the maximum or the optimum directivity, so this equation can be used. It's related to D. It's related to the diameter of the aperture size. So the aperture size, it cannot be changed randomly. So it also determines on lambda. It's related to the slant length and the wavelength together. So this is determined. So for a canonical hole, as we previously mentioned that the effective aperture equals, it has a relationship with the physical aperture, right? There is efficient, right? And for the canonical hole, the efficient purely equals 0.52 times EP. So usually for the optimum hole, right? So now let's assume a condition. So based on this equation, so if we want to increase the directivity of the hole, that means what we can do, we just increase the actual size of the hole, right? Then we can increase it. But actually, is it correct? No, alright. If it's correct, then we can, if we wanted to increase the directivity of our antennas, we can just enlarge it, and then enlarge, alright? But actually, it cannot, because there is a limitation on it. It's determined by, it also, as we mentioned previously, there is an axial length. This can limit the directivity. So, based on the measurements, when there is plot on it. So this is DC, okay? DC. Look no more, and this is the aperture size with respect to wavelength. So when we increase from this one, okay, from this one, here why we set it optimum for? Because this is the best point. This equation can be used to represent it. So actually, when we wanted to increase the aperture size, firstly, let me change color. It's gonna change. Firstly, so the directivity changes, then decrease. Increase it further, it will not always increase. It's gonna decrease. And however, how we wanted to increase this further again? How about if I wanted to increase it further, what I can do? There's a method. Increase the axial length. So for example, this axial length equals 1, then maybe centimeter. So if I want to increase it further, maybe I increase error node equals 2 centimeter. It increases, but also it has its own limitations, and then it decreases again. And then, if I want to increase it further, again also the increase error node to be 3. It also increases, but they're gonna be decreased. Okay, also. So the same thing as I'm increasing the error node equals 4. And so like this one. So that means if we wanted to increase our directivity, we need to increase the aperture D. All right. We also need to increase the axial length of the antenna. So now this equation. So we get, for example, many times we get the maximum points, and we connect them together. Connect them together, get a straight line like this one. And this straight line can be represented by this equation. Okay, it's not just one line, but there is the optimal point. So connect the optimal points of all these lines with respect to the axial length. We can get the expressions for this equation. Okay, so this is this one. So let's take what? Let's take an example to see how this can be used. So, for example, if we have a horn and we want it maximum, the optimum directivity equals 26 dB, and also we can get the D equals 8.8 lambda, and also the LC, the slant length is around LC is around 26 lambda. So we're going to get the maximum 26 dB. So, for example, if we set the so for example for the wavelength for the millimeter wave is around 10 gigahertz. The corresponding wavelength is how much? Around 30 centimeters, right? Am I correct? So that means the corresponding dimension D equals 4.26 centimeters, right? This one is around 878 centimeters. So for the 10 gigahertz, wavelength is only 3 centimeters. The slant length of the antenna is 78 centimeters. It's too high. Alright? It's too high. It's too long. So actually what we see is really is not so much, all right, so large. And what we need to do actually is we can, for example, if we want to reduce the size of the whole antennas but keep the same directivity, what we can do? Really, for the commercial components of of antennas, their size is much smaller than that. All right, that's because they sacrifice the directivity of it. They sacrifice this part to decrease the size of the antennas. But if we wanted to keep the same directivity, also we're going to decrease the size of the antenna, what we can do? Small one. Actually, for the optics, in optics, we already use the lens, all right, to increase the gain of the, for example, the lasers or the visible light. We use the lens to increase its gain or its directivity. So for here, also the same thing. This is the simplest method as if we wanted to increase the directivities, we add a lens. And sometimes, if we want to also the maximum directivity related to is it related is the collimated beam, all right? The from the spherical wave to the plane beam. It is collimated, something like that one, and we're gonna use a lens. Becomes collimated, and there are also some commercial products that integrate the antenna and the lens together. And sometimes, if you want it more flexible, and then you can use two separate parts, and then you can switch the lenses, all right? Change the for your applications or for your scenarios, and change it. Okay, so this is the demonstrations for the Hall antennas, and especially the canonical antennas. And later, I think we're gonna introduce the slow antenna. So for slow antennas, the most commonly device, for example, the leaky waveguide, right? A leaky waveguide, the parallel plate. We have two parallel plate. And at one plate there is a slot to edge. You're gonna really edge used to launch the radiation out from this slot, and which the well, for example, the dimension of it, the frequency of the radiation, and also the size of this device is always determined by the phase matching condition. Also, as impedance matching, all right? So, and we're gonna introduce it maybe after the holiday. So, yeah, I think we are done today. And happy the Mid-Autumn Festival. Okay, see you.
谢谢主持人。
再见。
再见，拜拜。
好的。
拜拜，再见。再见。